1.
All right. So hello everyone. Welcome to our presentation for our CS225 Final Project. Next page. So our project goal for this. So the goal of this project is to use two given data sets regarding the road network of San Francisco to create a graph, create a graph, and to create a DFS iterator that goes through the entire graph, to create a dexterous algorithm that is capable of finding the shortest path between any two given location on the graph, and to print out the graph to form a visual representation. Next page. So we choose to use an adjacency list to represent the entirety of graph because our graph has an incredible amount of data within them, making edgeless and adjacency matrix increase something very efficient when implementing a function such as incident edges and are adjacent. Next page. So for our DFS iterator, we utilize a combination of codes that is found in MP traversal and lecture notes. The reason we did that is because we decided to create an iterator instead of a simple traversal function. And our iterator is based on a stack which still allow the iteration to maintain a depth first nature while not using the recursion approach shown in the lecture. Next page and person.
So with our development, we chose to use Dijkstra's algorithm. Dijkstra's algorithm is an algorithm that's used to find the shortest possible distance between two different vertices. We decided to use this algorithm using an adjacency list to store all of the adjacent edges. Given a node, you get the adjacent edges, and we decided to use a priority list to implement the algorithm. So we chose this priority list because it seemed very straightforward compared to the other ways to do it, such as a self-balancing binary search tree or binary heap or pairing heap. And the way the priority list works is it keeps the shortest path. It keeps the shortest path so far at the top of the queue, so it's very easy to keep the shortest distance of the path organized, and so then you're able to just pop it off the top of the queue to get the path. We implemented this. Also, we used a struct to hold each vertice, and in the struct it held the node ID, the previous node, the distance of the path, and whether it had been visited or not. And with this, we were able to compare the path of the current node to the path of the neighbor and iterate through all the nodes to find the quickest path. And then the result of our algorithm was returning a path that had all of the edges of the shortest possible path between 2 points.
So for our development, as far as printing the roadmap, we had two algorithm choices. We could have chosen an image traversal method or a custom algorithm that involves 2 for loops. So we ended up choosing the algorithm that uses 2 for loops, which is on this slide here. So this algorithm starts by traversing across all of the edge IDs. And from these edge IDs, what it does is it creates these subplots per se. So on the screen here, if I draw a PNG, pardon the non-straight lines, but let's say this is our PNG and this is our edge. This algorithm here breaks each edge down into a subplot where across, it traverses these two bottom for loops here, will traverse across all of the pixels in the subplot. And if the slope between the start node, which in this example is here, and the point, which our random point is here, if the slope of this line is the same as the slope between the start and the start point and the start node and the end node, then that pixel falls on the line and then it's colored black in the PNG. And then once that is all, once all the edges are printed out on the PNG, then all the nodes are printed out on the PNG with a red X. And if the user of the function or the developer wants to print out a path between two nodes using Dijkstra's algorithm to calculate the shortest path, it will then call Dijkstra's algorithm to grab the vector of all the edge IDs that are part of the path between two nodes. And in the visual here, why is my, oh, close that first. On the visual here, you can see that the path is printed out in blue from one node to another. So this worked out fairly well, actually. And yeah, this is these are our printouts of the PNG or of the graph. And this one here is really neat because this path was between like nodes 20,000 and 40,000, which trying to map that, or trying to, you know, say what town or what city is node 20,000, we don't know. It's just, you know, we only have the number of the nodes, but as you can see, the blue line represents the path from one to the other. Conclusions, Arthur.
So all in all, we have we have set three main goals for our project. Four main goals for our project: to create a graph based on the given data sets, to create a DFS iterator of that graph, to create a Dijkstra algorithm that find the shortest path between any two nodes on the graph, and to create a graphical representation of the graph we created. So all in all, the first three objectives were completed quite successfully. The operations such as find adjacent incident edges and are adjacent are all seem to be functioning in constant times after the graph is created, and the DFS iterator seem to be returning the correct number of back edges and iterating through all nodes in the graph. However, due to the sheer amount of the information we have to take into account, the final visual representation of a graph is a bit rough around the edges, while the general sense of the San Francisco road network can be captured by the visualization due to the finer details we discussed. Sometimes the edges themselves are drawn incorrectly. Anyone else?
That's about it, I think. To add on a little bit with the failures, what Arthur was talking about with the edges being drawn incorrectly. As you can see, the graph is not near as pretty as the one portrayed here that we got off the website where we got the data from. Unfortunately, we don't really have any methods here. Well, there's no default libraries we can use to in the C++ default libraries we can use to print out a graph, but so we had to make our own. But as far as any options we learned in CS225, comparing the slopes of the 2 points seemed to be the best option, which unfortunately, you know, leads to these weird looking paths where they get really fat towards the middle and near the end of the edge. And this is due to the fact that the slope has a higher margin of error as you get further and further out from the start point. But other than that, we are very satisfied with the way our project came out, and we learned a lot, and that's about it. Thank you very much.